All right, so get this. We're talking fusion power today.
Mm-hmm.
Clean, limitless energy straight out of sci-fi, right?
Yeah.
Except there's a catch.
There is.
A really hot one. We're diving into this article, Beyond Tungsten. Scientists unveil game-changing materials for fusion reactors to figure out what it takes to build a machine that can contain a star.
It's a material science puzzle.
Yeah.
On an epic scale.
Yeah.
You're essentially trying to create a container that can withstand temperatures hotter than the sun's core without falling apart.
That's where this tungsten thing comes in, right?
Yeah.
It's been the go-to material for the divertor, the part of a fusion reactor that takes the brunt of the heat and particles.
Exactly. Tungsten is incredibly tough.
Yeah.
Which is why it's being used in ITER,
Right.
the massive experimental fusion reactor they're building in France.
Okay.
But the question is tungsten the best we can do?
And that's what's so cool about this research.
Yeah.
These scientists from EPFL's Marvel lab decided to go on a material hunt.
Using powerful computer simulations to find hidden gems that could outperform even tungsten.
Now, simulating a fusion reactor at full scale is a computational nightmare.
Oh, wow.
It would take more computing power than we currently have.
So they got clever.
They did.
Instead of trying to simulate the entire reactor, they focused on identifying the key properties of a material that would make it thrive in that crazy fusion environment.
Yeah. They started with a massive database of materials and put them through a virtual gauntlet. Think of it like a series of extreme tests designed to weed out the weaklings and identify the true champions.
Okay, so what were the tests?
First, they looked at the material's ability to handle heat. We're talking melting point thermal conductivity, how quickly it can spread heat and density.
Right.
Basically, they needed materials that could withstand the sun-like heat inside a reactor without crumbling.
Makes sense. What else did they look at?
They also considered how thick the material needed to be to withstand the heat without melting.
Think of it like building a wall, a thicker wall, provides better insulation.
So it's not just about what the material is, but also how much of it you have.
Exactly.
Rad.
They then went through and eliminated any materials that had already been tested or had known issues.
Gotcha.
Finally, they used advanced simulations to test two crucial things: how resistant the material is to erosion from all the particles bombarding it,
Right.
and how it interacts with tritium.
Tritium, that's a key ingredient in fusion, right?
It is.
But what's the problem with the material interacting with it?
You don't want your divertor soaking up tritium like a sponge.
Oh.
That's a safety concern, because excessive tritium retention can cause all sorts of problems. It's like trying to contain a fire, but your fire extinguisher keeps absorbing the flames instead of putting them out.
Okay, so after all those tests, who were the winners?
Well, some of the usual suspects made the cut, like different
Wow.
forms of tungsten, diamond, graphite, and some transition metals.
Okay.
But here's where it gets really interesting.
Hold on, I gotta catch my breath. This is intense. What did they find?
They found materials that nobody expected to see on this list. Tantalum nitride and boron nitrogen-based ceramics materials that weren't even on the radar for fusion reactors before.
Wait, so they found materials that could be even better than tungsten?
Potentially, yes.
Yes.
This is huge because it opens up a whole new world of possibilities for designing fusion reactors. We could see more efficient and durable reactors in the future, all thanks to these unexpected champions.
That's incredible. But how did they even think to test those materials? They seem so different from the usual suspects.
That's the beauty of this computational approach. They were able to cast a wider net and explore a much larger range of materials than traditional methods would allow. It's like having a super-powered magnifying glass that can see the hidden potential of materials that we might have overlooked before.
So they're not just finding new materials, they're revolutionizing the way we search for them.
Absolutely. This research is a game changer, not just for fusion energy, but for material science as a whole.
Okay, I'm trying to wrap my head around this. So we have these new materials that could potentially outperform tungsten. What happens next? Do they just start building reactors with them?
Well, it's not quite that simple. There's still a lot more research to be done. Remember, this study focused on specific properties that are important for the divertor?
Right, the part of the reactor that takes the heat.
Exactly. But there are other parts of the reactor that also need to withstand extreme conditions. So the next step is to see how these materials perform in those other areas.
So it's like a puzzle where they're finding all these amazing pieces, but they still need to figure out how they all fit together.
That's a great analogy. And beyond that, they need to figure out how to actually manufacture these materials on a large scale. Some of them might be difficult or expensive to produce, which could limit their practical use.
It's like finding the perfect ingredients for a gourmet meal, but then realizing you don't have the right kitchen tools to make it.
Exactly. But the good news is that the Marvel Lab is already planning their next steps. They're going to use even more sophisticated simulations powered by neural networks to get a more complete picture of how these materials behave under realistic fusion conditions.
Neural networks, that's artificial intelligence, right? Are they teaching computers to design fusion reactors?
In a way, yes. Neural networks can analyze massive amounts of data and identify patterns that humans might miss. This allows them to create more accurate and realistic simulations, which can help us better understand how these materials will perform in a real-world fusion reactor.
It's like having a team of super-powered scientists working around the clock, crunching numbers and running experiments.
That's a great way to put it. And on top of that, they're going to start incorporating the effects of neutron bombardment into their simulations.
Neutron bombardment, that sounds intense.
It is. Neutrons are released during the fusion reaction, and they can cause damage to the materials inside the reactor. It's one of the biggest challenges for fusion technology.
So they're not just looking for materials that can handle heat and particles, they also need to be resistant to neutron damage.
Right. It's like designing a suit of armor that can withstand not just swords and arrows, but also lasers and explosions.
Okay, so this research is giving us a much deeper understanding of what it takes to build a successful fusion reactor.
It is. And it's also highlighting the incredible potential of these new materials to accelerate the development of fusion energy. Imagine a world where we can power our homes and cities with clean, safe, and virtually limitless energy from fusion.
It sounds too good to be true, but this research suggests that it might actually be within reach.
It does. And it's not just about the technology itself. It's about what this technology could mean for humanity. We could solve the energy crisis, combat climate change, and create a more sustainable future for generations to come.
It's a pretty inspiring thought, but let's bring it back down to earth for a second. You mentioned earlier that there are still challenges when it comes to actually producing these materials on a large scale.
That's right. Some of these materials might be difficult or expensive to manufacture, but that's where innovation comes in. As we learn more about these materials and how to work with them, we'll develop new techniques and processes that make them more accessible and affordable.
So it's not just about the materials themselves, it's about the entire supply chain and manufacturing process.
Exactly. And that's where collaboration between scientists, engineers, and industry leaders is so important. We need to work together to overcome these challenges and turn these promising materials into a reality.
It's a reminder that scientific progress isn't a solo effort. It takes a global team of brilliant minds working together to achieve something truly groundbreaking.
And that's what makes this field so exciting. It's a collective endeavor driven by a shared vision of a better future.
This deep dive has been an incredible journey. We started with a simple question. Is tungsten the best material for fusion reactors? And now we've uncovered a whole world of possibilities with new materials that could revolutionize the way we generate energy.
And we've also seen how computational materials science is transforming the way we discover and design new materials. It's a powerful tool that can help us unlock the secrets of the universe and create a more sustainable future.
It's mind-blowing to think that we're on the cusp of such a transformative technology. But as with any major scientific breakthrough, there will be challenges along the way.
Absolutely.
Yeah.
But the potential rewards are so great that we can't afford not to pursue this path. The quest for fusion energy is a journey worth taking, and every step forward brings us closer to a brighter future.
It's wild to think something so massive, like a fusion reactor,
Right.
could depend on these tiny little materials.
It is.
It's amazing. It really shows you how everything's connected in science.
Yeah.
A breakthrough in one place can have a huge impact somewhere else completely different.
What I think is so fascinating is that
Yeah.
it challenges our assumptions about what we think could even work as a material inside a fusion reactor.
Right.
For so long, we thought tungsten was it.
Right. It was the best.
That was the gold standard.
Yeah.
But this is showing us that there might be other things out there
Yeah.
that could do even better.
And not just better, but maybe fix some of those safety issues we talked about.
Right.
Like with the tritium.
Exactly. Getting soaked up. Tritium retention's a big deal. And if these new materials can help make reactors safer,
Right.
more reliable, that's a huge step forward.
Totally. So where does this leave us? What's the takeaway for someone like me or, someone listening?
I think the biggest takeaway is hope.
Okay.
This research shows that fusion energy is getting closer.
Yeah.
It's not just a dream anymore. We're finding new materials, coming with new techniques, and doing things we never thought possible.
It's like watching a sci-fi movie, but in real life.
I know it is.
Yeah.
And the best part is we don't know what's next.
Right.
Maybe we'll find even better materials or a whole new way to use fusion.
Yeah.
I mean, the possibilities really are endless.
So what do you think? Could this stuff speed up the timeline for fusion? Is this something that we might actually see, working in our lifetime?
It could happen. I mean, there are still some hurdles to get over, like figuring out how to make these materials on a huge scale.
Right.
And keep testing and refining the technology.
Oh, yeah.
But even just talking about this,
right,
thinking about fusion power being a real thing, that shows how far we've come.
I'm feeling really optimistic after this whole deep dive. It's really inspiring seeing these researchers and how dedicated they are. They're not just working on a science problem, they're working on something that could change everything.
And that's what I think is so great about science.
Yeah.
It's about going beyond what we know and then using that to create a better future for everybody.
Well said. So to everyone listening out there, what are your thoughts on this?
Yeah.
Did this change how you see the future of fusion?
Mm-hmm.
Let us know.
And while you're thinking about it, maybe do some exploring of your own.
Yeah.
There's so much to discover in the world of fusion energy.
Absolutely. That's it for our deep dive into fusion.
Thanks for listening.